Hello everyone, this is Dr. Hopkins making the next in our set of videos for 472, and in this video we are going to discuss free energy of reactions. So notice we've been talking about free energy for quite a while in this course, where we've been dealing with the free energy of phase transitions or the free energy of other processes, but now let's do a general relation to chemical reactions. So the Gibbs free energy of a reaction, obviously at equilibrium, the dG is equal to 0, right? So our spontaneity criterion, if we're at constant pressure and temperature, if dG is equal to 0, nothing's going to happen. We're going to consider this general reaction. We have two reactants, two products. We have the stoichiometric coefficients. And then we know that the Gibbs free energy follows the Gibbs-Duhem relation. So here we have, it's just the sum of our chemical potentials times the change in moles, and all of that is equal to 0. In other words, none of them are going to change independently. If there's a change in a reactant, there's a change in a product, and so forth. And so we take advantage of that, and we're going to collapse all of our change in moles into an extent of reaction parameter, which we're going to label with this xi. Okay, so our change in moles is the stoichiometric coefficient, because they may change faster. If this is larger, there more of A are involved in the reaction, it's going to change faster or have a larger change than, say, B. And so the number of moles is the stoichiometric coefficient times this extent of reaction parameter. So basically we're saying that there's only one reaction, and it's either moving in this direction or this direction, and we're going to define it with one parameter, not with four different numbers of moles. So if that reaction is proceeding towards products, the d xi is greater than 0. And so likewise, less than 0 means it's proceeding towards reactants. Okay, so let's go for this general reaction. Then we can define the free energy using the Gibbs-Duhem relation, and then we substitute in our extent of reaction parameter. So we have our stoichiometric coefficient, our extent of reaction parameter, and then the chemical potentials of the four components. And then we define a reaction free energy. So if we're going to divide through by this d xi, and we make this a partial derivative, holding pressure and temperature constant, this partial derivative of the Gibbs free energy with respect to the extent of reaction is our reaction Gibbs free energy. And it's related to all of those, the stoichiometric coefficient times the the chemical potential. So if this Gibbs free energy of reaction is less than 0, so if it's negative, that means we're moving towards products, or it's an exergonic reaction. If it's positive, we're moving towards reactants, then it's endergonic. And if the reaction Gibbs free energy is equal to 0, we're at equilibrium, and there's not going to be a change from reactants to products or vice versa. So let's look at our chemical potential. That was the one point. So we've got a stoichiometric coefficient, a chemical potential. This is an equation we've seen many, many times. We've defined them in most cases. We're always defined versus a reference chemical potential. And then we have the chemical potential expressed in terms of activity. So for the total reaction, then we add in our stoichiometric coefficients, our chemical potentials, the Gibbs reaction free energy, and we're going to combine all of our standard chemical potentials into one overall Gibbs reaction energy plus RT of the natural log of Q, this reaction quotient, which is the product of all of our activities. So it's the product of our products over reactants, all raised to their stoichiometric coefficient. So if we have a gas phase reaction, our concentration is expressed in mole fraction. We still have the activity coefficient, and then we have activity if it's in solution. We have the activity coefficient once again to account for non-ideality, and then we're going to express our concentrations in terms of molar concentration. So we're going to have a molar concentration divided by some standard molar concentration, okay, so that all of our activities are basically unitless. If we have a solid or liquid involved in our reaction, these activities, the activity versus the activity of reference, is the same, so it's 1, And so effectively a solid or liquid does not participate in the reaction quotient itself. So as you can guess, at equilibrium, the reaction quotient is what we define as our equilibrium constant. So that's the case where if we're at equilibrium, this term, or the reaction Gibbs free energy, is equal to 0. So our standard Gibbs free energy is equal to minus RT natural log of K. So that's related to that equilibrium constant. So if we are in solution, we have our activity coefficients, products over reactants, and equilibrium constants, products over reactants. Of course, I've neglected to divide out the standard state, but none of these would have units. If we're in gas phase, typically they're labeled as Kp. We have our activity coefficients to account for non-ideality and the mole fraction, but always products over reactants. So let's look at the temperature dependence of Gibbs free energy. So we have automatically we have a temperature dependence here. So there is an RT term to this, but that was the definition of our standard Gibbs free energy of reaction. So we can rearrange this so the natural log of K is equal to minus delta G over RT, or K is the exponential. So we remove the natural log, the exponential of this term. We also know that at constant temperature and pressure, the Gibbs free energy is delta H minus T delta S. So there's another temperature dependence, okay? And we're going to substitute that in here. And then our natural log of K reduces to this delta H over RT plus delta S over R. And that's what we call the Van Hoff equation, okay? And now we can evaluate the slope of the Van Hoff equation is this, the change in the natural log of K. So we make this Y and we make this 1 over T. The slope of that is our enthalpy of reaction divided by R. So we can determine if we have equilibrium constants and temperatures for our reaction, we can determine both the enthalpy of reaction and the entropy of reaction just by plotting them in this Van Hoff equation. But we'll also see, based on how the equilibrium constant changes with temperature, you can see that if we were to have an endothermic reaction, so that's greater than 0, then this K would increase with increasing temperature. So if we have an endothermic reaction and we add temperature, we are favoring products in that case, okay, in terms of the enthalpy. If we have an exothermic reaction, one that gives off heat, then the K will decrease if we were to add temperature. So we add temperature, we move the reaction towards reactants. And we can apply all of these principles to the numerous reactions, chemical reactions that you might run. But all of this is kind of the thermodynamics of our chemical reactions. So until next time.